But so this is the work which I primarily did over my 5 years of PhD. So I'm trying to give you a summary of why table is an interesting data structure to work on and what are the interesting pitfall opportunities there. So let's start, and thanks for the introduction. So the top title is still, which stands for semi-structured tables, inference and reasoning. So let's first look why one should look for semi-structured data. So first argument I gave is it's present everywhere. For example, you purchase your products from e-commerce. So there are product attributes value tables which are there. Then when you look at your taxes and financial reports, you file your taxes, they also are in the form of tabular format. So they are present in finance also. And then whichever teams or sports you support, they have score tables which highlight and give various statistics about event or player statistics, etc. And now, lastly, we write a lot of papers, and in that we present our findings and data in the form of table also. So we can see that tables is present everywhere, and it's an important data structure which can be studied, and NLP models can be used. Second point, I feel why tables could be interesting is because they hold large and diverse information in a very compact form. So you can use that for comparing and contrasting. For example, you have seen when you buy products, you have similar products, and then you can see which one is better, what are the differences. For example, in this, there is a iPhone comparison of two types on various attributes. So you can look at that and see how things are good. And then from the modeling point of view, NLP models have struggles as well as it's an interesting data structure for them because tables implicitly require a lot of multiple types of reasoning. So this I will also emphasize in the upcoming slides. And it's require you to understand the connections between the entries. For example, a simple question like, what is this table about? Anyone? The first table, what is it about?
Yeah, it's in horses.
Yes, that's a good. It's a sports table which is about horses, and it's an equestrian sport. And so just by looking at this, we are able to recognize. So there are obviously clues. For example, sports is there. There's horses there. So this Desar's table is basically a sports table, telling more information about the sports. Now, to understand this table, we need to understand like what does contact mean in terms of sports. So contact mean like whether you can touch players or if the sports require contact in the sports or not. Similarly, mixed gender here mean like can both men, women can participate in this event or not. So, and then there is, you see they have keys, but they also have values which are anyway in the form of Boolean. They are dates, and they can be any free form text. So understanding the connections between the term is require different types of reasoning. Also, while doing any task, for example, if I want to do question answering or inference on this, it requires combining these structured knowledge as well as looking from the world knowledge. For example, we know what does mixed gender kind of mean in terms of the sports data. So this another the table can be in multilingual form also. For example, this is a boxing table in the bottom, which is in French. Another example, if you see iPhone, I can basically ask a question which is, can I want to query like, can you suggest an iPhone under $1,000 with 6.1-inch retina or a higher display, dual MP ultra-wide camera, latest processor in dark brown. So you can see like it requires us to go through multiple rows of reasons, and basically so under 5,000, under 1,000 like only these are eligible candidate. Then 6.1 and higher mean like these, and then I want better camera. So these are the two options I have, and then the latest processor mean the one which are at higher number, which is 830. Also, you see there's a lot of multi-model thing. For example, the color is basically not represented as color, but in text form, but the color actually present. Similarly, the like if face ID or touch ID is basically represented in the form of symbols here. So now once you have this, if a model can process this, basically we are able to answer these questions really well. Now, generally there are two kind of semi-structured data, which is one is more of an entity-centric thing, which is like this New York Exchange table where there's keys and values, and the values are any free-form text, which can be dates, boolean, or any kind of free-form text, and their attribute. And there are tables which are also a longer tables, which are generally we have seen. For example, this is United States House Representative, where there is a header and then there's multiple rows aligning around that. So my focus of work was mostly on the bottom part because that requires a lot of common sense and word knowledge. And the above table also require, but most of the question around there are like mathematical and SQL oriented, so which is involved with semantic parsing. What I'm looking for more is direct natural language task around it. So when I started doing this work in 2018 and 2019 onwards, so there was a lot of work on NLP around unstructured text. So there were models. Now we obviously have large language models, but these were the primary models during that time. There was a lot of challenging benchmarks. There was a lot of extreme data sets, and also there was a lot of leaderboards to evaluate stuff. So when I started working on this all things were missing in that area. So it was not many resources and work around this. So we delved into this, and again, why NLP? Because it requires comprehensions of entries in the table and the connections between them. For example, what does mixed gender mean in terms of quotes? And we thought it's a good testing ground to see how models reasons with structured or semi-structured data. And it requires multiple types of reasoning, multiple role with common sense, and also combining various structured information. So my work primarily deal with is developing techniques and resources to close this gap in handling complex data types, such as semi-structured table. So the main hypothesis which my PhD work revolved around was we argue that reasoning on such semi-structured data is particularly like the entity-centric tables, although simple for humans, but difficult at the same time for NLP models, because they were designed only for unstructured text. And to make correct inferences, even when they do, they can make it for very wrong reasons, which I think many of you are aware of. Like models do things, but they might not be doing the correct reasoning or logic behind the answer. So to address these challenges, some of the things which I focused on were incorporating knowledge and making model focus on the right relevant parts in the semi-structured evidence. So let me give a quick overview of the work which I did during that time. So the first part we involved still was creation of data set. So we created this data set called InfoTabS. So which is basically you have semi-structured tables like this their source table. And let's say you have a claim, which is basically you have to determine whether it's true, false, or maybe true or false, like entail, contradict, or neutral based on the premise. So this is very similar to the standard NLI task I'm sure all of you are familiar with. The only difference here is the table, the premise is not a sentence, but it's a semi-structured data. It's a fact which is presented in the form of tables. So we also extended this to multilingual aspects, so where the table can be in other languages apart from English, which we call XInfoTabS. From the first work, we realized that these models doesn't do well on structured data, and one part of why they don't do well is because they are not able to understand the meanings of terms in the table, because the table are not sentences, so they just provide very brief context about the stuff. Obviously, the having information about other keys help, but still the model doesn't understand what does mixed gender mean, or what does contact mean, or what does a volume mean in a financial tables like New York Stock Exchange. So the first work focus on basically how do we address this by adding of knowledge externally through retrieval and other techniques. We also recently dealt with problem of this information mismatch. So what we found interesting is like there is not just everybody I think is aware there's less amount of data in other low resource languages specifically, but we also find that the data in low resource languages is also outdated the facts they are presented is not just lesser, but they are also very outdated. So there is this huge multilingual information mismatch around this. So you have, for example, Wikipedia data, and so there may be pages which are missing from Wikipedia data. There can be tables which are missing from Wikipedia data. There can be tables which are present, but they are not updated in the other languages. And interestingly found that obviously English is the most data available on the Wikipedia in terms of article and all. But we also find the disparity between the number of editors for English versus other languages even huger. The gap is even larger. So slightly that the data on the web for other languages might be outdated. So can we use NLP tools, techniques which we're developing to do something around this filling of this information gap across multilingual language? We also dwell into problem of probing. So this problem is very familiar. Like people have seen, like model get the right answers, but we don't know if they are doing the correct reasoning around this. So we study how can we probe models on semi-structured data because of the underlying structure which is present in the table. For example, we know that these all are independent facts, and we can basically do a systematic probing of the table. For example, I can just shuffle the rows in this entries and then check if the model is robust to that shuffle, which can become harder in an unstructured text because the structure, the sentences are basically in canonical orders. But in tables, there is more because of the structure and independence of the rows. We can do a lot of several types of easy probings, and creating data around that is also easy. So we also study how does models look at the right evidence, does they react well to new tables, what about that? And the basis of that, we found one problem which was prominent in the models, which is basically they didn't look at the right evidence. So for example, to say the statement is true, both men and women can compete in the contact lens sports of dressage, the model need to look definitely look and focus on the row contact and mixed gender. So if the model is not looking at these two rows, however it get the answer, it might not be the right way. And lastly, we found that, okay, one way of creating data set is we can have annotators do a job, but there is also data sets created by others for various other tasks in semi-structured data. So can we basically repurpose them for our tasks? So basically more the merrier kind of approach for data learning. As we know, most of the deep learning models require a lot of supervised and unsupervised and supervised data. So can we basically get this supervision from other ways, so which require like recasting? For example, there's a data set around tabular QA, can we use it for tabular and vector? And then also can we use logic around, because of the structure of the table, can we use logic to create much more data? So in this talk, I will not cover all the parts, but I will try to cover some of the parts which I found interesting and useful and still relevant in the current context of LLM. So let's first start with the InfoTabS task and the data set. So the task, as you know, is very similar to the NLI task. The difference here is basically we have a premise, which is a table rather than a sentence. And we want to say whether a statement is true, false, or cannot be determined based on the table. These are some examples. This you have already seen. So both men and women can compete in the contact lens world of dressage. Now this is true because this contact, no, mixed gender, yes, and we know dressage is a sports table in general from looking at the keys. This is another example. The same dressage athlete can participate in both individual and team event. So at the first glance, it looked like a true statement because there is a row which called team members, and it says individual and teams at international levels. But the language have also effects. For example, the same dressage, I'm not true whether the same individual can be both in the team and the individual events. So there is individual and team events, but can the same athlete participate in both and true? Given the table, we are not aware of that fact. So this is undetermined or neutral. Lastly, there can be information which can be verified from multiple sources in the table. For example, FEI governed dressage only in the US. So first we see FEI is an international body. So this statement kind of coming false, and also then there is presence of dressage in the worldwide. So this basically the statement is a false because of these two rows. So this I already covered, it required information. So this task was perfect because it's checked a lot of reasoning ability. It also required common sense and world knowledge. Like both men and women understand it's related to mixed gender, contact class code is contact, and there's other sports, for example. In this paper, we also found that when we do basically testing, now this actually become a standard. We basically create multiple test sets. So because we know that model can be spurious, can learn spurious correlations and do well on test sets. So we also created multiple test sets with the data set. So we created an adversarial set 2, alpha 2, which we call, where we basically take the existing premise which the human wrote and ask them to flip the label by just minimal changes to the sentence. For example, for the table in like a movie table Inception made a profit of over 5 million. It can be changed to Inception made a profit of under 5 million. And now the label will change. However, the reasoning aspect of the sentence and the relevant row and everything remain the same. We also see if, let's say, these tables require numerical and other kinds of reasoning. If I give tables which are from other domains, like keys which are not seen in the data set, so this like cross domain or zero shot domain. So, for example, we take tables from rare category like airport, disaster, and see if the model can generalize to that. Now, one question which I think is still interesting in the context of LLM is how do you represent a table to a model? So in this was now seeing like one idea is we can convert the table to an unstructured form. For example, we can take each key and maybe convert it to a sentence like this. And this we can do through a model, or we can do like by simple rules like. So this is like this look like a less grammatical sentence, but it's still a valid sentence. The equipment of dressage are this. So we can use simple rules to convert each rows into sentences and then put them in a paragraph and then use the model for multiple paragraphs. Now, one thing, if you have noticed, like the whole table can be very big if you do like this, and not all keys are relevant to a hypothesis. So one idea one can do is on this fact is only take some similarities between the hypothesis sentences and the sentences we have generated and keep the things which are more similar. So instead of like take top 5 sentences or top k sentences and just keep them. So this we call as premise as a sentence. And one main reason we created this because most of the models which were there were sentence NLI based. So they were the length of the premise was almost equivalent to one or few sentences. So we want to get our data. If you check models which are like trained on sentence NLI, we want them to be as close to the sentence NLI stuff. The other is forgot about the data, the unstructured part and just linearize with respect to where you just take the key and value and separate with some appropriate element like key colon value, and each row can be separated by semicolon. So this is just like linearizing the table, and the main title can be like title colon research and then semicolon, like you can just linearize it. So we check what kind of reasoning. So we take some sample of the InfoTabS data set and see what kind of reasonings are there. These reasonings are adapted from the glue and superglue. So superglue and glue come with annotated set of all reasonings and their definitions. So we modify them and make it adopt for our data set. And in this process, we also create some new simple things which are missing. For example, if the information is coming from multiple row, we call it a multi-row reasoning. If the information is just simple extraction, for example, in the table, I just say what is the highest governing body or highest governing body of dressage is this, then it's like simple lookup. It doesn't require any reasoning around it. And then also there were things, especially in neutral, where we have subjective and out of table information. Like subjective, we can basically read dressage is a very good sport. So we don't know it's very good or not. That's very subjective opinion. And we can also have out of table information, which is got better. So we take subsample the dressage and manually annotate 3 annotated what kind of reasoning they contain. So a few highlights of this, we see that the data set contains a lot of common sense and knowledge, which was interesting. It has other reasonings also like multi-row, 4F, numerical, temporal, so which was interesting aspect. We also found that the neutrals, although are more on the subjective and outer table, because that's the easiest way to form a neutral. But then there was also neutral coming from other reasoning types. So there were neutrals which were created not just by subjective opinion or out of table, but also by other ones, which was interesting point. Now, so we took Roberta large model and first we check hypothesis only baseline. To the surprising, that baseline itself was doing very well on the data set, around 60%. So this is again related to the spurious correlations which model run. But at the same time, that baseline was not doing very well on the adverse set, which is the alpha 2, which is adversely flip label, and alpha 3, which is out of domain. So that's the model, this baseline although is good, but it's still not running. And this is a 3-way classification task. We see when we add the full table and the correct table, the model obviously started doing better. And we also find that if we just linearize, that's working better than even like converting to paragraph, which was interesting. One aspect can be that the paragraph conversation are more not very grammatical structured. But if you look overall, the humans are still quite above the performance. We also take this data set and see if we can convert this to a multilingual setting. For example, there's the boxing table in English, and now I have a boxing table in French. So the main, and then we can hypotheses which are also multilingual. So when we started this thing, we thought of maybe we can just extract table in multilingual language from the Wikipedia page. But then we found that only 10-20% of the data will be extracted like this because the tables are almost missing or they are very outdated from the other Wikipedia page, which led to the problem of InfoSync, which is, can we use this to basically make update table in the French. The main highlight here of this work was how to do table translation, because tables are not a full sentence, so they have minimal context. So we developed a pipeline for doing that. The main two things which we use here is, once we separate each row, so we do independent translation of each facts. So we separate each rows and then translate them separately. And secondly, we found that if we just translate them barely, it won't help because the context is missing. We also add some context. For example, this is a sports table, and see if that context help in translating it better. Another thing we found that there are also things like, for example, there's a table called breakfast in America. Now I don't want to literally translate this, I just want to transliterate that thing. So we also do a NER tagging before even doing anything, otherwise we will have tables which are translated where it should be transliterated. So we did this approach, and although this is not a perfect approach, we found that many of the tables we translated are pretty good on human evaluation and other metrics. Now, seeing that the models were not doing very well on this, we thought of how we can make them do well and discuss various challenges around that. And one way of doing well is basically we can add knowledge. And in this, we think of two directions of: one, we can add implicit knowledge, or we can have explicit knowledge in the form of definitions or from knowledge graph or other sources. I will give you an example how knowledge can help. For example, this is a New York Stock Exchange. The task is the same, given a table and then statement, you have to say whether it's entail, contradictory, or neutral. Now you have to understand that what does volume mean in context of this table. So here the volume, if you look, can have multiple definitions. For example, a volume can be the thermodynamic definition of volume, which is the space required to in the space. Where we are talking about here, volume is the financial context, which is equivalent to the number of security that are traded in the thing. So we found that if we make model aware of the right context definitions, then the model can do better on the task. And to do that, what we simply did is we take existing resources like Wikipedia or WordNet. We take the definition as well as some illustrative examples of where those definitions are used. For example, we take a context where volume is used in the terms of capital market, and one example of volume which is used in thermodynamic sense. And then we embed them using BERT, and then we also embed the volume which is there in the hypothesis or the premise and check the similarity. Similarity of the example with the example embedding we get from the for the volume from the definitions. And if the example embedding which has the best match, then we take the definition corresponding to that example. So this way we are able to disambiguate and add correct definitions. For example, here we are able to add volume is total number of security that was created during a given period of time. Now, along with the premises, we give this as an extra knowledge in the end and see if the model can do better. So this was like very simple technique because we just have a pre-processing where we append extra information and we use external knowledge to append and improve the model. But we also look at some drawbacks of these techniques and how this can be improved. And we look at this problem in larger context of what do you mean by knowledge addition. So there are three things which involve a kind of knowledge addition. One is what you want to extract. So we want to extract contextually relevant information from the external source. So this can be Wikipedia, WordNet, or other knowledge base or any other source. We also want to see how we can represent this additional knowledge. So we have, let's say, the knowledge. We have the definition of volume. Let's say, how do you represent that to in the correct form? And then let's say you are able to represent, how do you integrate these knowledge with the model? So how will you fuse that model, that knowledge with the model which you have? So on the basis of that, we propose a novel architecture called Katan's-Kilby LSTM, where we look at these three aspects. So this is where we use LSTM plus transformer to add knowledge. And why we looked at specifically a new architecture rather than just append knowledge. So some examples why that approach could not work. So one thing is like the definitions can be very long. For example, if I just want to add a definition of, let's say, this is a table which is converted in paragraph. So you see there's a key called guide and I add the definition of guide. So you can see this is very technical and wordy definition. And I just want like a very simple and what does guide mean in terms of this. Secondly, the ambiguation may fail sometimes. For example, when we add the definition of born, there were examples, very few, but where born is basically got confused with the born scientist, which is added the definition of born scientist. So this adding of this definition, and also if you see the premise was this length, but when I add the knowledge itself is this length. So it's bigger than the premise to start. So maybe this approach has issues. So now to handle this, what we look at is more structured knowledge bases, sources of information. For example, one of these is knowledge graphs. And so instead of taking like definitions from Wikipedia, WordNet, one can basically use knowledge graph to get definition. So the idea here is like we take pairs of relations which are there in the hypothesis and the table and see their connections in the knowledge graph and then try to exploit that to add relational knowledge. So we take the hypothesis and the premise and see what are the words which are there in the hypothesis and what are the connections with them in the knowledge graph phase. And this basically led to like a simple triplet like California is a coast. So California at location coast. Now I can take this triplet and use a simple, convert to a simple sentence and then use a transformer based approach to embed them. And we use this approach and we've also find like you can use even simpler model like LSTM and all embed this knowledge and can be efficient as well as do better. So we found that this approach actually benefit. So if you don't add knowledge, obviously you are not performing that good. If you just use the definition thing, you are better. If you just add the token level stuff, and that's not very beneficial, but if you basically take the knowledge graph, this knowledge, and also integrate that with proper embeddings, they are more helpful. Specifically, when you have like adversarial sets, where like alpha 3, where the keys are not ever seen in the training set. And also in the low data regime, when the data is very less, we found that the knowledge addition actually helped model doing better. So we found that because of knowledge addition, we improve on several reasoning types like ACL, multi-row, numerical, subjective, and quantification. Another benefit of knowledge addition, which we found implicit, is it helped the model to focus on the right relevant row. For example, like the statement, Jeff Bridges started his career as a young child. Now, we know as a human, it's very easy for us to, okay, we have to look his year active or the start of his career. And then we have to look at his birth date and then determine whether he did it in, whether he started as a young child or not. Now the knowledge itself focuses on the, like for example, the born is focusing on the young, the active is focusing on the child. So the knowledge itself sometimes gives us the right clues to link to the right hypothesis. So this knowledge addition itself sometimes help us in implicitly getting to the right evidence or help the model to focus on this. So we found also one of the reasons that it's do much better on the multi-row reasoning category. If anyone has any question. Next, okay, this is like we have external sources and we are integrating knowledge. But can we do something implicitly to use, for example, the knowledge which is stored in the pre-training process of models? So for this, we adopted a very interesting approach of pattern expertly training. So the task, if you look at the pre-training, is done by masking models on unstructured text, and the task which we are doing is like the entailment, which is a classification task. What if we basically merge this into a single task of closed form? For example, in this case, we can just take the premise and the hypothesis and mask the prediction to predict whether it's yes, no, maybe, which is equivalent to entail contradiction. Now, this way, we have basically converted the task, which is in the form of, first was the classification, now into a same task of close masking approach. And if you see that now in this, we can also pre-train our language model by masking the things in the premise and hypothesis for the task also. So we can mask three things, which is one is the label, the premise, and the hypothesis. And this helps us in basically retrieving better facts. For example, Breakfast in America is an album. That is, we can mask is an album and it's try to recall that from the surrounding context. So this help model in getting appropriate relevant context. And also we have basically, instead of two different tasks, the task is in a closed form way. So we found that this types of merging the two tasks in a closed form single approach help in two ways. So if we do this, first is if we evaluate the knowledge before and after the classification training, we found that the model recall much better its factual information. For example, Breakfast America is 46 minutes. And then it also recall the relational information really well, like what is the connection of 1979 with Breakfast in America? It was the release date of that album. So doing this closed form style approach, we found that models do better things. So earlier we found that if you just take the earlier model, it has some information about these facts, but when we train on the classification task, this information is somehow lost in the parameters. So in this approach of like this, where we do the same, train the NLI and the masking approach in single way, then we found that the model recall much more better these factual information, especially on the relational side, which is the left side. You can see that the model recall more knowledge compared to earlier approaches. And this has also implicit benefit. We found that this help in model doing particularly better on the adversarial sides. So the model is now also doing better on the downstream NLI task. The task is same, data is same, but we are doing much better on the NLI task, especially on the alpha 3 and alpha 2 side, which is out of domain and adversarial side. Another benefit we found is like this approach is robust to a lot of like perturbations. For example, if you have spelling mistakes or if the location and number changes, then the model is much more robust to those compared to earlier approaches. So there are more results. Any questions? Next, we looked at the question of is the model doing the right reasoning, and for this we analyze this statement, which is not just related to tabular reasoning, but it's general. Any evidence-based system, reasoning system, should demonstrate expected predictable behavior in response to control changes to the input. So let me pass the three main thing which is there. What is the evidence-based reasoning thing? What is expected predictable behavior in response? And what are the control changes we can do to the input? So what I mean by evidence-based system is like both men and women can compete in the contact lens post of dressage. Now we know this statement is true, and we know why also, because there are two rows in the table which says contact is no and mixed gender is yes. So these are the evidences around it, and now there is also reasoning involved, because if the contact is yes, then the statement will become false. The reasoning that contact should be no and mixed gender should be yes is also the reasoning which is there. Now the problem with the models is they do not give both of these, so they don't provide why they are giving the right answer. So why is they are looking at the right evidence, and also they don't give the reasoning steps which we are trying to do with now LLM models. Both things. So we want to see how a model generates something and also how the model arrive at some answers. So these two things we are looking around. So we thought of, okay, let's see if this existing models which we fine tune are doing this thing or not. So one way is we can probe this model by control changes. So let me ask you a question. Let's take the same statement. Both men and women can compete in the contact lens post of dressage. And now let me remove the row contact from the table. How do you think the prediction should change? So if I have the same table and I remove the row contact from the thing. Anyone? Neutral, correct. So the label should become neutral or undetermined. Now this we call as control changes. So here one control change is what I did is deletion of a row. So we study like how can we study these, like insertion of a new row, deletion of a row, or shuffling of rows affect the model performance. And we found that because of the semi-structured data, we have certain rules which we can use to exploit this changes, which I will go in the next. Now we know that the model prediction should change to neutral, but is there any way we know how the model prediction should change? Yes, we do know. So the claim is we can look at this automata to determine how the model prediction should change. So this is T for true, F for false, and UN for undetermined or neutral. Now we know that any deletion of information cannot make something which is entailed to contradict. So deleting information should not make something which is true to false. Similarly, something which was contradict before, after deleting information, it cannot become true. So it can at most go to neutral. So we know that any deletion of random row from this table, the model prediction should either remain true or become neutral, but it cannot go to contradict. Now we can use this fact to basically probe models if they are looking at the right evidence. So we did three kind of systematic probing. So one of them I already briefly explained is basically we look at if the model looking at the right evidence. Secondly is the thing which is I think highly studied is what happens if we make changes to the hypothesis. Does the model do the right thing? For example, the alpha 2 set. So this is like annotation artifact. Third is what if the information is not something which is there in the world? For example, we have a factual fantasy information or we have counterfactual information. For example, dressage was not a horse sports, but it was something polo sports. So can the model still, given the evidence, reason on that? Because we are saying, given this table, you have to reason on the fact. So this is like counterfactual instances. So in the interest of time, I will just look at the evidence selection part, which I like more in my work compared to others. So in this, what we basically study is the model drawing the right inference from the premise thing. And one way to is we can systematically alter the table by simple operations and see if the model deterministically correctly change the inference label. And then we see how many times it doesn't follow that rule or it gives invalid label changes. So alter the premise table is basically the way we deleted the contact information, and simple operation is like deleting that contact row. And deterministically change is basically it deleting a row should make it either entail or neutral. It cannot be contradictory. So, and we check if we do this thing a lot of time, how does the model react to this? So we checked a lot of things, a lot of like we added row, we updated row, we permute row, we insert new information and see how does the model react to that. So I will just go over some of them in the interest of time. So one thing is like we can just take a row, which is a random row from the table and delete. So we can do a lot of perturbations on the input premise and check. What we found is that model do sometimes make something which was entailed to contradict. So the model doesn't follow this automata, and sometimes the true statement can become contradict, as well as there's a neutral statement initially, which become basically both true and false, which should not happen, because anything which is neutral before after deletion should either should also remain neutral. It cannot be true or false or entail or contradict. So based on this logic, we count how many times the model is making this mistake, and we found that the model is making the mistakes. Furthermore, we found that if we have some metadata, for example, we know for this hypothesis, these two rows are relevant, then we can further fine-grain the automata which we have. So we can say anything, if we delete a row which is relevant to the model, then the true statement can only go to neutral, and the false statement more likely will only go to neutral. There are cases it can also remain false, but very, very few chances. So we know that most likely if we delete a relevant row, then definitely it should become. Now, once we did that fine graining, we found that model do mistakes at very fine other levels. So we found there was looking like the model was very good on this example, but it actually is not good because many times it changes information, which after deleting a relevant row, it still remain entail or contradict. So most of the time we found that the model just stick to its original label, which it shouldn't do that if we basically delete a relevant. So we found that no, the models is not looking at the right evidence, and this is the issue. Similarly, we found that model do rely on this hypothesis-based correlations which are there to get to the right label. And we also find that many times model use it pre-trained knowledge over the evidence you ground, which is again a problem which we are trying to deal with retrieval augmented to do the right things. So although like this was on Roberta and before, but I think these questions are still on large, on not just stable, but all the things which we are doing on LLM nowadays. And then obviously the problem of reasoning is separate if we even look at the right thing and do the thing. So model do sometimes recall heavily on it pre-trained knowledge. So this, how can we unlearn or basically make it more grounded on the evidences we provide? That's a problem also. So
just a quick question. So are you increasing the weight of the like the newer evidence here? Like the tables?
Correct.
Like it has some text, like it has some learning from the pre-training. So what do you do? Like, which one is more important?
So yeah, this is an interesting question. So there is not a very fine line what is common sense, what is world knowledge, but the more important is the evidence we provide. So if the evidence says that dressage is a non-sports event or it's a polo sports, let's say, then it should ground on that fact, because the task we gave is the same model. Given this evidence, is this statement true or false? Okay. So then it should definitely, obviously, if we have open-ended tasks, obviously using it parametric knowledge is one aspect which it should heavily rely on. Okay. Now, if we will do retrieval augmented, which is again, the retrieval is right, then it should heavily rely on that. If the retrieval is wrong, then it might use more of parametric knowledge to get the right answer. Anyone else? So, in the interest of time, I will quickly sum up on this. So this is the task of model not looking at the right evidence. And one approach I already discussed is we can make sure that the model look at the right evidence by only keeping the right evidence in the NLI task. For example, if we somehow make model aware that for hypothesis H1 and H2, only number of listing is relevant, and similarly for H3, only volume is relevant, then maybe the model doesn't look at the wrong rows and get the answers. One way you can do is basically make the table prune, given or remove the distracting information, and give that only to the model. And then for doing that, you can basically use alignment-based algorithms to do the task. So we found that when you do this distracting row removal, the model performance increases, especially for longer tables and tables which were the model not pre-trained on and all. So we found that if you keep the premise as smaller and remove distracting information, then the model do much better and focus on the right evidence. So we create a method where we split the task of NLI into two parts. One is evidence extraction. There's also a similar work like information bottleneck, where you basically the first task is given the hypothesis and the table or the big piece of evidence. You only find evidence which is relevant to this, and then you basically do the inference. And we found that this is pretty good. If you don't do any extraction, the model do worse. If you do extraction in unsupervised way, it do help, especially not on the training thing because there it hurts more, but especially on the adversarial and out of domain or setting, which is alpha 3. If you do supervision types extraction, then the model do even better. And if you have human, which is extracting, which is the oracle. So this is like oracle training and oracle testing on extraction. This is oracle training and supervision during the testing time. And we found that the models do even better. But again, as a human, we are still doing much better on the task despite the model. So we implicitly do this task of evidence extraction and looking at the right evidence and making inference better. We also did some experiment on counterfactual tables where we created other tables, but here the main idea is like you have to create tables which are consistent by themselves. For example, the born date cannot be before the died date, or the marriage date should be in between the born and the died date. So we also experimented on that. And this is something also we use to create more synthetic data in this. So I will skip that and move on to the recent work which I'm doing. So some of the recent direction, I think they are also a little bit old now, but like which I'm exploring is this multilingual semi-structured data. So one we already explored is we want to create more data around table. And one problem which we found was interesting is this problem of information synchronization. So now, for example, you have a table, this is a table in English of the same person. And now I take this is from the Wikipedia info box and the same person in Hindi. One thing you can clearly first see that the information here is more than this, just by number of rows. Secondly, you can see that the information here is sometimes outdated or represented in very different form. And so there's a problem of how we can use this information to basically update this information. So this is also like knowledge or information transfer, and I call it information synchronization because we have devices and we want to synchronize information. So here we are synchronizing across multiple languages for the structured data. So there can be problem of missing information, there can be outdated information. Sometimes the information can be split. For example, the born has 3 information: the born place, sometimes there's birth name also, and the born date. So the other table might have those information in split way. So it can be 1 to many, many to 1 nothing also. Then the key is how we represent in one language versus how we represent in the other language can be very different. What we call alma mater may be something else in the Hindi or other language. So there is a normalization issue when we basically synchronize the information. And then there's also issue of structure. So this is like key value, there may be, and then there is subheading like scientific career here. There's no subheading here like scientific career. So this has the hierarchy thing can also be different across 2 pieces. And then there is also problem of erroneous entity linking. We found that many times this tables in other language have something which means something totally different at the keys. So this work we got it recently on finding. And to handle this, we basically look at two main ideas. We split this task into 2 parts. One is alignment, where we see the information which is there, how they do align with the information in the current thing. Obviously, we don't want to just translate the table because first, we don't want to replace the human written data if it's correct. Secondly, we want to learn from the human data and make updation of the new data. So we basically look at like algorithm for similarity, and then we keep something from high precision and relax high precision high precision, low recall, and then relax the rules to get better recall with keeping precision as good. The updation side was pretty tough because we don't know where the information will flow from here to there, especially for the outdated information. But they can be clues. For example, there can be dates or there can be numbers. So we make some heuristic rules for doing that. But we are now looking for better techniques because now we have LLMs which have their own knowledge and information. So maybe there is a better way of transferring those information. One interesting thing we found is that the model information flows from both sides. So it's not just English which is updating the other languages, but we also find for some of the things, especially like the local languages of the entity. For example, this Prime Minister of India, maybe that has a very good page in Hindi compared to English. So the information can flow in other side also, and the information can flow in both sides. So now let's see what work I'm currently doing at Penn. So some of the things which I'm looking at is, especially now focusing more on the LLM side, is temporal information. For example, like you have a table which has a lot of temporal entities in them. How does the model reason on them? Can it connect those information and do something? And this information can be in implicit form. For example, how many position does he hold in a particular year? Or what position does he hold when somebody was something else? So it can be event, multiple time, or it can be very simple as what is the affiliation in particular date. So it's like 1953 is before 1965. So his affiliation mean political party. So basically he's independent before 1960. So these can be interesting and challenging questions. So here the challenge is how do we do temporal reasoning plus the structure information and relates parts. And the relation can be across large different spaces. So we created a data set around this paper recently got into MLP, and we study how LLMs do on that. And they are not bad actually, they are doing pretty good. So especially GPT-4 and 3.5, they are doing pretty good, but they are still very far from humans which can do this task. So we have two domain, head and tail. We also find that obviously the training is not even. Obviously the tables which are rarer, the models struggle more versus there we are more frequent or more happening. So if you take categories which are rare like airport and all, like versus you take very popular category, very popular tables in particular categories, then the model is doing much better. So also the one interesting fact is, since this is all Wikipedia created, one aspect is looking at counterfactual aspects in these and seeking if this model using it pre-trained knowledge or grounding on the table again to do the task, because the information is everything in the table and you can use temporal reasoning, common sense and numerical thing to get things. So how and can we do that? And if we can do something around temporal and numerical training with knowledge graphs or any other way to do better. I'm looking for more ideas that people have. Can we do better on such kind of tasks? Then we also look at, so information also changes with time. For example, this is the place I did my PhD, Salt Lake City. And now one thing which is true is the water resources are depleted, the mayor has changed. So what about information which is changing and you want to answer something beyond, between this and this, how much is the population growth? Or how much is the population rank change, or how much is the decrement in the area? So that require basically taking two sources and maybe going back in time and seeing things around. Or they may be written somewhere in the text and the model know it and answer, and that's the most likely this will happen.
For this one,
Correct.
is the change in land versus water because the lake is shrinking?
Correct. So this is another example. So this,
I would have thought that those
Yeah,
things would
so
be
this-
relatively static, but that's
Yes. So this information is evidence that the lake is shrinking, and which was there in the news also, like the Salt Lake City is vanishing, Salt Lake is vanishing. So this clearly shows that what changes are happening, and maybe they give us more insight of what's going right, what's going wrong. And these changes can be like something which doesn't change at all. Like for example, the country is same, the state is same, and there can be change which are periodic. For example, the POTUS likely changing after every 4 years, or there can be non-periodic and rampant. And also the reporting time of these changes, where the changing actual happened, might be very different. Something can suddenly become popular and it is more talked about and the changes happen. But it might not be, maybe an event which happened very long back. This is true, like many of the Wikipedia pages are created when there is something big or like something significant happened then only. So the reporting time as well as the thickness may not be aligned. So that's another problem of how these things are. So lastly, I'm looking at tables which more complex things. For example, tables which are hierarchical. So tables within a table, especially if you look at our like tax reform form, that's not a simple table. There are multiple columns of different sizes. Some are bold, some are not bold. How can you understand that? There can be symbols in the tables. There can be other form of thing, and they can be infographics also. For example, these have like colors, this thing. So how do you reason on such complex data, which is merging two things? And the structure gives you some information. For example, these are all of same type, they represent something. These are all colors. So it gives information about things. So the structure can help maybe do the stuff better or not better. So, and maybe the multimodality as the information can act. There's another example. For example, this is a Wikipedia table I take where basically how many states this a party with a lotus symbol one. So now you have to reason on the lotus symbol is basically this party called BJP and what they work. Then there can be like information in the form of charts, maps, and other forms. So they can be merged in the table or they can be separate. How do you reason on that? So that like I want to think, and I'm doing some more interesting. If anyone is interested or thinking about those problems in larger context. So like charts, question generation of complex aspects. Can we make LLM less hallucinating and more grounded on the data we retrieve? And many of these also have application like catalog expansion from reviews, and also if you are interested, we can talk more on that aspects. Lastly, like I want to thank like many of the work was done when I was PhD at Utah, especially the first part which I presented, and you have the Utah NLP lab. Also, this is not just me, but there's a lot of collaborators and a lot of people behind even the funding aspects involved in making this one. Yeah, thank you. Anyone? Yeah.
Thanks for the great talk. It's very interesting. I had a question about, I think the second piece of your talk where you added knowledge to the model. I was wondering, for the very interesting example you gave where knowledge was added for things like die and born, how did you determine which pieces of knowledge is not known by the model at inference type?
Another good question. And so I'm not sure what, so this is again, so one, there's a lot of work which see what LLMs tools, but there's also like, how do you evaluate those models? So people did mask things and try to see if the knowledge if the model knows those facts or not. But then they are also very highly sensitive of how do you frame the knowledge extraction part. So work which says, okay, I can give a statement and mask like, what was the bond, or you can do question answering also, or you can mask, for example, the bond date of someone and then see if the model can retrieve that well. But again, knowing and using is very different thing also, which I realize. So even with LLMs which are there here, they might know a lot of things, but when given in a task situation where they have to evoke that knowledge, will they evoke that or not? That's another interesting question which is there. For example, you're doing a planning task, and if you say, okay, do this thing, and it gives a set of instruction, but maybe it doesn't evoke something specific knowledge around that. So that's also another problem which is there. So, but you can probe on some of those aspects, whether it knows or not, and then can it evoke or not? Then the two questions, if you can answer, then probably you can answer your question. But it's still, but I think that how do you, but nice.
I have two questions. I actually not coming from the NLP field. I come from the computer vision field. So bear with me if I ask stupid questions. I have two questions. So the first one is you have a touch about the multimodal at the end,
Okay.
and I'm wondering like use image and you also represent table in the beginning, and the table may come from different formats, and I'm wondering. If you use image rather than the sentence as input, is the problem harder or easier?
That's a very good question, which I'm exploring a bit now, because recently there are a lot of models which can directly take structured information. So you have seen GPT-4 can take a receipt, so they can do better OCR and all. Secondly, they can understand image. So it's interesting. One of the students then checking if they can take something like this with this image plus text together, and there can be multiple images. But what we observe from the recent is like if there's more than one image piece thing, then the models start breaking very bad. So up to 2 images it still do well, like Lava 1.5 or GPT image model. But if you have more images and all, then it's hard. And also like giving this information to the model, like maybe I can give the images all together and by give positional embedding. So those are also interesting questions. How do you represent this complex data to the model? Even the hierarchical table, it forgot about images. Should we give information about a sub-level or should infer by itself of the spacing? So those are interesting questions.
Thanks, Bhavani. And also for the table itself, like without images, because I'm recently used GPT-4 to like translate my input, my uploaded table image to LaTeX, for example, and it do very good job. So yeah, so I'm wondering if you input image rather than the sentence, just with the table you showed before, like without image, is that easier to understand the structure of the table or harder?
So one thing which we recently observed is there is subtle differences. Like for example, if I convert this image to a text versus I convert this image to a knowledge graph, which is more structured, then the performance of model do vary. But models are pretty good in understanding like key value kind of tables and inferring from them. That's good at GPT and all these models. But when you go to more complex tables, they started facing issues and correcting things. And also when I found that this is not just the problem of like the table, but also about the domain you're checking. So if you go for tables which are very rare and all, with the rarer keys and all, then the model struggles. So we don't know whether it's doing well because of like the training it has given. So they have seen this data, or it's because of like they just understand the table. And also how do you represent? So if I recently we did some experiment where give the table and knowledge graph. And it just stayed on very good amount of knowledge graph. We found that it's pretty doing better with knowledge graph compared to table. So the representation do matters, the input to model, which we have seen that even the prompts change after model.
Yeah, thanks very much. Another question I have is, how long, like how far the current large language model to read and analyze the whole financial statement of a company?
Okay.
For example, yeah, and what's the challenge?
Yeah, so there is a huge progress. I would not say it is not huge. So we can take like Claude and all, you can take a big document. Even I have tried some complex receipts and all, and it's able to do that. So we have good things. I'm worried more of the reasoning aspects in that. So can it relate the information? So it do OCR and get the table and structure well, but it still can't do the. For example, one interesting thing we tried is like maps. And can it understand map? We have a human understand maps, and even say even if we don't, if we highly annotated, we also find they are very sensitive to the data which they are doing. For if you change the color codes, then the model started failing. So it looked like it's doing really well, but you make subtle changes, then the model started to be failing. So which we as a human can do the things with. So I'm not sure again on that aspect if they are doing well. But yeah, as look like they are very good at extractive tasks, organization tasks. But I think on the planning, reasoning, and understanding more complex relations between structures, there I think you can clearly see there are some issues around that.
Yes, well.
Anyone?
So I'm wondering if you like consider the role, so for like your last 2 points about like, tables being updated across languages or like updated across time and like having different information across languages. I wonder if you consider like the role of the temporality when it comes to like the multilingual table stuff, right? Because it would make sense that if you go back to that like Indian English example, it would make sense that, or like I would think that it would make sense that like maybe for this, I forget what the example was, but was it like Australian?
This one?
Oh yeah, so like, a lot like if you could consider the role of temporality when it comes to like updating all these different fields, like maybe the information synchronization like back to English, to the other way, that could be explained due to like, people in India caring more about like things that are not.
Correct. So
Yeah, so I think that's like a natural combination of these two.
yes, so we did make to solve this task some heuristic rules, and one of the rules we have is like temporal aspect. So if
Oh, yeah.
let's say for company table, if the revenue mentioned in one of them is like 2020, profit 2020, like generally there are sometimes dates given there. So and in some places it's like 2010, so the information will definitely flow from this. This is common sense plus temporal English. So there are some rules which are there, but sometimes it's very hard to decide what is relevant and not, and maybe that plays more the recent retrieval aspect. So information which is more recent might be the right one, something like those could be used. There's another aspect of temporality, but what we know is recent or not, if there's no timestamp mark on the information. So how will you know that? And this again brings the problem of multi-view. So if you have multiple places of information, which one is correct? That's again a problem, and this I think is a huge problem with retrieval augmented LLM. You can retrieve wrong things also. And with LLM, I think we will have coming future might be having more information with night, but it's actually correct, and we will retrieve them, provide answers on them. Knowing what is right, wrong, and become much more prominent. And temporality and common sense can have big role.
Yeah, and then like LLMs are specifically trained on data up to a certain point, right? Whereas like information
Correct.
changes. So
Yes. But with tools and retrieval augmented thing, I think these are changing. But how well they can, again, this being the problem of grounding now. Even if you give it the right information, will it use the pre-trained knowledge or the recent information? So that's again a problem.
Yeah.
Again, with the probing aspect there. Can we making sure that it uses the right knowledge and information around it?
yeah, I'm working on a project that's like very relevant. So I'll have to like talk to
so we
you
can-
later about this work.
Yeah.
If no more questions, let's thank Vivek again.
Thank you. And feel free to email me, contact me, talk about anything or any other thing which you are doing.